Tonight's topic then is maximization and minimization, which we can jointly call optimization. I'll just spell it. It has a strong analogy to calculus 1. So if you remember that and can just sort of extend it a little, I think you'll understand this pretty well. It's the same thing in more dimensions than what it really is. So we'll say first, in calculus 1, what do we have to optimize a function? We were given a function of one variable, a real valued function of one real variable, y equals f of x. Yes. And on an interval from a to b, we can consider this function, and if it had any point c1 where the derivative was 0, actually let's just draw this off forever for now. Any point, say c1, at which the derivative is 0, or here's c2 where the derivative is 0, at the bottom of a valley, was called a critical point. Right? Those were very important because they were all the candidates for relative extrema, where the derivative is 0, or you can have a point like this. Over here, you can have some point like that. Here's a corner where the derivative fails to exist. Here's a local minimum here, so we can call this C3 a critical point, where f prime of C3 does not exist. But a critical point was a point where the derivative is 0, also called a stationary point, or the derivative didn't exist. And every local maximum and minimum occurred at a critical point. Right? What's a local max and min? It's where over some interval, no matter how small, about the point, say from here to here, or with this as an interior point, that's the smallest value. It's less than or equal to all the other y values. So on there, it's less than or equal to all these other y values on this piece, so it's a local minimum. Here, this one is a local maximum because on some interval, no matter how small, for this interval of x values, this is the bigger than or equal to all the other values. Remember that? That was local maximum then. And then you could have critical points like this, C4, where there's a horizontal tangent line if I draw it right. But it's neither a maximum because it goes up on one side and down the other. So here's a point where the derivative doesn't exist, and then C4 is another stationary point, a point where the derivative is 0. So every local max and min occurred at a critical point, but not every critical point corresponded to a max and min. We call this an inflection point. Well, it is an inflection point, but not every inflection point is at a critical point. So we'll just say there are critical points where you have a minimum and maximum, and points where you don't have a relative min or max. That was calculus 1. Now, what are we going to do for functions of more than one variable? Really, we just want to look at functions of two variables because after that, we have to draw them in four-dimensional space or higher, and it's too hard, but the concept still carries through. Right? So in calculus 4, we'll instead say the following. Remember, a critical point here was where the first derivative was 0 or does not exist. What shall we do for a critical point for a function of two variables? Z equals f of xy. If let's say as critical point x naught y naught if the two derivatives, partial of f with respect to x and x partial with respect to both 0, or if at least one of the partial derivatives doesn't exist. Well, it's similar to this. It's just with two derivatives because you can take partial derivatives in different directions.
We can't see that low on the board.
Okay, thank you. Let's see if I can fix it. That better?
Perfect.
Thank you. Nice to know I'm not talking to myself too. All right. Well, that'll be a critical point. And then there's a nice analogy. Theorems too. Theorem says, well, first we need the definition, I guess. Definition says that a function of two variables, f of x, y, has a local min, just like this one, you want to bottom out or top out. A local minimum, right? X0, x naught, y naught. If on some disk at that point, no matter how small, with positive radius, let's just say open disk, just because we now this on some disk where this is in the center. Same criterion. F at that point is less than or equal to f at xy for all x on the disk, including that point. So this is less than or equal to f of xy for pen is going. All xy in the disk. So instead of having it be the minimum over an open interval, you can make it over, let's say, an open disk. It doesn't matter. Closed is good too, because if it's closed, then it has an open one inside. Right? So just an interval, no matter how small. In this case, just a disk, no matter how small. In this case, and maybe it's worth drawing a picture, I suppose. Really, the picture is the way to figure this stuff out in the long run. Gives you such a great intuition. Z equals f of xy is a surface. Maybe it looks like that. Oops. Now what you want instead of a derivative equal to 0 is both partial derivatives equal to 0, or at least one doesn't exist. In our cases, we're pretty much always going to have the derivatives exist. So what we're thinking is, here's a point, x naught, y naught. Here's another point, x naught, y naught, x1, y1, where both partial derivatives exist, are 0, right? And what you see geometrically here is a horizontal tangent plane. F partial with respect to x at this point is 0. F partial derivative with respect to y at this point equals 0. It's a horizontal tangent plane. And same thing over here. Horizontal tangent plane is the concept. Now, this actually doesn't guarantee that the partial derivatives exist in all directions, but this is the general picture when it does. So this is f partial with respect to x at x1, y1 equals 0. Partial with respect to y at x1, y1 equals 0. So those are two critical points, but you could have another spot here, like you could come over here and maybe within this thing you have a spot where it goes up to a spike, right? And it's not differentiable at a spike. So here's a point here, maybe x2, y2, that's also a critical point. So these are all critical points. Two of them are critical because the two first partial derivatives are zero, and you have a horizontal tangent plane, but one of them is a point where you can't take the derivatives. So that's what we're thinking of visually when we write this stuff down. Now the theorems, I told you this will be a lot of analogy to first semester calculus, and in some sense it's a little easy. That's the definition. What do you think the theorem is? For when it has a relative min-or-max, a local min-or-max, those will mean the same thing. Local min-or-relative, relative min-or-max.
Dr. Stapleton,
Yeah.
I have a hard time hearing you when you're looking away from like whatever you're looking at.
Yeah, just
Yeah.
summarize what you were saying.
Thank you. Well, I was saying, what's a theorem do you think that would come up now for functions of more than one variable? It's an analogy to what we did for calculus 1. On calculus 1, we have that every local min or max occurred at a critical point. Same thing here. Every local or relative max or min, jointly called relative extrema. If it's a relative max or relative min, you can still call it a relative extrema. And the book will use that term. All right, let's call it local extrema to use the same word. Switched there, didn't I? Local maxima are all called local extrema. Occurs at a critical point. Not every critical point is a local extremum or gives a local extremum, but they all occur there. And remember, the relative maximum is not the point. The relative maximum is the z value that occurs at that point, right? Just like the function of one variable, the actual maximum was how high the y value got, but the critical point was the x value. Similarly here, the critical point is x0, y0, but the maximum or minimum is the value of z that goes with it. Here's an interesting picture. It puts together some of the things you've already seen. Remember this saddle-shaped thing that we call the hyperbolic paraboloid, one of your quadratic surfaces? Suppose we have that, and then maybe it goes off, and the surface switches, and it has a dish down here like this. This one would have a critical point right here at x naught, y naught, right in x, y, z space. This is some surface z equals f of x, y. But this point is called a saddle point, not because the shape is a saddle. The saddle is the classical picture of it. But if it's concave up in one trace, take a vertical plane like this. If you can take a vertical plane and get this trace, it's concave up. And then you take another vertical plane in some other direction, like this direction, and the trace is concave locally. Then you say, oh, it's a saddle point because it's not a maximum min. It goes up in one direction and down in the other. So this would be a saddle point. This is a critical point, right? Because it has a horizontal tangent plane. The derivative is zero along this trace and the other trace. It's a critical point. But it's neither a maximum min. This one, however, at the bottom of the dish has a horizontal tangent plane, and it's concave up in all directions, right? Oops, if I draw it correctly. And so this one has a relative minimum, and the minimum value is f at x1, y1. If I call this point at which it occurs, x1, y1. So two critical points, x naught, y naught, and x1, y1, where there's a horizontal tangent plane. One of them is a saddle point that is concave up in one direction, concave down in the other. One of them is a relative minimum, it's concave up in all directions. Okay, so that's the first thing. You do like you did in calculus 1. You say, I can't check an infinite number of points, but now I know I just have to find the critical points, right? Just check the critical points. So usually there's a finite number of those that I can just check them. Once I'm down to not very many points to check, how do I check each one to see if it's a relative mix or min or max? Drawing a picture doesn't prove it. Maybe if I got in close enough, maybe it wiggles and it's not really a min or max, but it's locally some saddle point. Well, again, what did you do in calculus 1? You had two tests. You had a first derivative test. This is what you did in calculus 1 again. I'll just draw this on the side. You don't need to do this. When a function had a derivative, you could check the derivative a little bit on the left and a little bit on the right. And if it was down always on the interval on the left and up always on the interval on the right, the slope was positive over here, negative over here on some interval, no matter how small, then you knew that it was a local minimum. On the other hand, we had something like that, where near the critical point x1, on some interval, no matter how small, it was always, the derivative was positive on this side, and this side of the interval, and negative on this side, then you know it's a relative maximum. F of x1. We call that the first derivative. How that for functions of two. But it's so ad hoc that you have to check all directions with this stuff. Right? You can imagine in a plane, when you've got a surface, you have to check the traces in all directions. There's an infinite number of them. It's too hard in practice. So we're not going to do the first derivative test. Maybe that's kind of good. You have one less test to do, huh? Instead, we had a second derivative test where you just had to check the point. At the first derivative test, you had to check on an interval about the point. If the derivative was positive on one side, negative on the other. The second derivative test for a function of one variable said this: if you had a point where the derivative was 0 or didn't exist, well, the second derivative test, it had to exist. And the second derivative also existed there. If the second derivative is positive, then it was a relative minimum, thinking of concave up. If the second derivative is negative, then it's a maximum, thinking of concave down. And if it's concave up or down on an interval, if it's second derivative is positive or negative interval, then it is actually concave up on the interval. But all you need is the second derivative at the point. You don't need an interval like this. So it doesn't technically have to be concave in there, just at the point. Right? All right, so you can check the second derivative at the point, and that's what we're going to use for these functions of two variables. We'll use an extension of the second derivative test, called the second derivative test for functions of two variables. So here's the big theorem for relative extrema, local extrema. This one. Yeah. F of xy has two continuous derivatives. On its domain. Which needs to be open so that we can take derivatives from all directions. If you get on a boundary of a domain, then you can't take derivatives in some directions. So if it's continuous, if the second derivatives are continuous in the open domain of definition, then you have the following extension of the second derivative test in calculus 1. You first compute D, which is fxx, the second derivative with respect to x, times fyy, the second derivative with respect to y, minus the mixed partial derivative fxy squared. And since it has two continuous derivatives in an open domain, fxy and fyx are equal, and so you can put either one here. Let D be this number. And you evaluate this at the critical point. Which you find by just finding whether the derivatives are both zero or don't exist. So I can put this on here, evaluated at x0, y0, and y x. That just means pulling the point after you find the second derivative. But really, this is so messy here, it's nice to leave this off. All right. You compute that. Now, at each of these points, if the second partial with respect to x at that point is positive, and D is positive, what might you guess happened? It's a little tricky, but it's not too bad. What happened in calculus 1 when the second derivative is positive? It was concave up and you had a local min, right? Same thing here. If fxx is positive and D is positive, then f, the original function at x0, y0, is and it sounds counterintuitive for a second. In calculus 1, why would positive be a minimum? Well, positive means it's concave up, right? So it's bottoming out. 2, if x at the critical point, again, just like the second derivative test in calculus 1, you only have to plug into one point. You don't have to check it on a region like in the first derivative test. That's what makes the first derivative test so bad for functions of more than one variable. You have to check all these points, an infinite number of points in a disk, all these directions. So if x is less than 0 and D is positive, then f at x0, y0 is our local maximum. All right. What else can happen? Could be that D is less than 0. If D is less than 0, then it's a saddle point, it turns out. Neither a max or a min. Because remember, saddle point means it comes up in some directions and down in others. There's the second derivative test for functions of two variables. It has this one additional restriction. You have to compute D first. And D tells you whether the concavity is consistent. If D is positive, the concavity is consistent. I only need to check the second derivative in one direction. I can take a directional derivative. I can take a directional second derivative. I can take the second derivative with respect to x, second derivative with respect to y. It doesn't matter. So you don't have to use fxx here. You could just as well replace this with fyy, and it works. Because D tells you that the concavity is consistent. So if fyy is positive, so is fxx and second derivative in any direction, actually. So we'll put fxx here. That's exactly what calculus books does. But you can check second derivative in whatever direction you want. Often fyy is easier to compute. Now, if d is greater than 0, that means the concavity is consistent. And so if xxx is less than 0, then it's concave down, locally at least. And you have a local maximum. So negative second derivative is a local maximum, just like in calculus 1. Then if d is less than 0, that tells you it's a saddle point. The concavity changes depending on what direction you're going. So those are the three criteria. And then if d equals 0, you don't know. I won't write that down. The book might. I can't remember now. Sometimes they put that in just to be explicit. But if d is equal to 0, it can be either, is the point when they write that down. Any questions about that one? That's all the tools for relative maximum. We still have to do the global maximum, just like you did in calculus 1. This is number 11. It says locate all relative extrema and saddle points for this function. F of x, y equals x squared plus xy plus y squared minus 3x. I wonder what are the relative extrema, relative maximum. Let's call them local again. I keep changing words there, don't I? Local extrema and saddle point. Right? What do I do? Just like calculus 1, right? You find all the candidate critical points, then you put each one into the second derivative test. That's all we have to do here. This is a second degree polynomial. It has derivatives of all orders. We don't have to worry about the derivative not existing, and that'll be the case consistently on the homework. We don't, for this section, worried about where the second derivative doesn't exist, but you do want to keep that in mind that if you actually had a place where the derivatives, partial derivatives didn't exist, you'd have to check something. Check all directions kind of stuff. See how good your memory is by erasing the theorem. I'm sorry, it's just a small board. You can't put everything up. These are long problems. Last many years ago, where we had made it in the nursing building, and all the boards were tiny like this. And I'd write the first part of the proof. Any questions? Second part, any questions? I'd get 5 boards down, and any questions? And boy, you just can't ask a question 5 boards back. It's all gone. So I like the boards. And when we get back to class next week, weather permitting, we should be meeting in person for those people who want to, beginning on Monday. So it's in person unless they say us otherwise. And anybody who wants to can meet online, of course. If you've been exposed to COVID, then don't come. Just watch online like this. But I'll do it in the classroom to get better images, right? More boards. How do I find the local extreme and saddle points? 1, find the critical points. 2, plug each into the second derivative test, right? Set the critical points are now by setting both partial derivatives to equal to 0 instead of just the one derivative equal to 0, right? So I said fx equals 0. Let's compute these. Partial of f with respect to x. We use this brief notation here. Can't use prime because right, there's derivatives in different directions. Partial with respect to x is 2x, right? Plus y plus 0 minus 3. Treating y as a constant in there, right? Now what's fy partial with respect to y? 0 plus x plus 2y plus 0. So it's x plus 2y. Those are the first partials for this polynomial in 2 variables. Right? Now we need the second partials because we're going to apply the second derivative test, right? F of x partial with respect to x is just 2. Then I can compute mixed partials, right? Fxy or fyx, they're equal. Remember the second partials theorem, the partial derivatives when it's continuous in an open disk are equal everywhere in that open disk. So we take partial with respect to x, and minimum with respect to y is 1, right? Partial with respect to y is 1. Similarly over here, if I took partial with respect to x, I'd also get 1, right? And then fyy, so this is the mixed partial derivative, we call it. Fyy partial. So d in this case is just a constant. In general, you have to plug the point in. It won't be the same number at every point like this one, but we just picked a real easy example. D is fxx at the point. Oops, I forget. I'm sorry. I first have to calculate my. Like I said, I need to do the critical points and then the second derivative test. So the critical points are where these are equal to 0. 0 equals fx. 2x plus y minus 3. That's partial derivative with respect to x equals 0, and 0 equals partial derivative with respect to y. X plus 2y. So how can I find the solutions to this equation? In general, these happen to be linear equations, but in general, you get two nonlinear equations and two variables, and there is no general technique to solve them. However, we got linear equations. There is a general technique to solve them. And, there are other equations you can solve too, right? You can solve quadratic equations in one variable, for instance, right? But if I call this equation 1 and this equation 2, here's how you solve for the critical points in a lot of these, is you add a multiple of one equation to another, right? Another way is to solve for one variable in one equation. I put x equals minus 2y and substitute it into the other equation. Nothing wrong with that. You can do that too. Solve for x in this equation, plug it in for y in x in this equation, get the equation just in y. If you have more than two equations, though, that tends to take longer. Substitution with 3 or more equations generally is tedious. 4 or more is just about out. It's so complicated. But it works for 2 very well and works for 3 okay. I'm going to instead do this, what we call elimination. Anybody ever heard of Gaussian elimination before? Maybe you took linear algebra early. Gaussian elimination is an orderly process that solves every system of linear equations. Ax plus by equals c. Ax plus by equals c. Any system like that, it solves it or shows that it has no solution. And so it's really great. So that this can always be done, but rather than use strict Gaussian elimination, write out all the rules, I'll just say it's pretty easy to do this anyway. Just add a multiple equation to one equation to another to eliminate a variable. Suppose I want to eliminate y, for instance. I could add minus 2 times the first equation 1, equation 2, and that'll eliminate y. I'll add minus 2y to plus 2y and make it 0, right? So that's what I'm going to try and do. Minus 2 times this one is minus 4x, plus x is 3x. Oops, I forgot the left side first. Minus 2 times 0. Oh, and you know what else I should do? On this one, I put the fx equals 0. I'd like to put the 3 on the other side just to keep all the constants together. Let's write it like that. You don't have to, but if you keep the x's with the x's and the y's with the y's and the constants with the constants, then they add down easily, right? Math is the same, but you're less mistake prone. So minus twice equation 1 plus equation 2 is minus 6 plus 0 is minus 6. Then minus 2 times this one is minus 4x plus x is minus 3x. And then minus 2y added to 2y is 0 as I wanted. I eliminated y. I've got minus 3x equals 6. Evidently, with 2. Now, that's not a critical point. The critical point is an xy coordinate. Both these derivatives are 0. This is just the value of x that's required. It means every critical point in there has x equals 2, and that's it. Now I can plug this into either equation. Let's put it into 2. That looks like the easier one. Both of these problems are long. Then I get 0 equals 2 plus 2y. Evidently, y equals negative 1. That's our critical point. There's only one. Only one place where both these equations are satisfied, where both partial derivatives are 0. It's at the point x equals 2, y equals minus 1. If I All right. Now I erased my derivatives on it, didn't I? Erased too far. All right. So there's only one critical point It's a 2 minus 1. So there's only 1 point to check with the, there's only 1 point to check with the second derivative test. What do I have to do? 2, apply the second derivative test. Critical point, there's only 1. And I first compute D, right? D equals fxx at the critical point times fyy at the critical point minus fxy squared at the critical point. Well, let's look these up again. Erase my derivatives. The second derivative with respect to x was 2 at all points. The second derivative with respect to y was 2 at all points. And the mixed partial derivative was 1. So d is equal to 3 is positive. We don't care its exact value. We just want to know if it's positive or negative for this test. Now we compute fxx or fyy, whichever is easier. Because d is positive, they'll both be the same sign. Fxx is actually equal to 2, is positive. And then by equation 1, since d is greater than 0 and fxx or fyy is greater than 0, we have a relative minimum at this point. Let's call it local minimum at this point. The value of the local minimum, though, is the original function at that point. So I just have to plug it in now to see what the minimum is, right? How high does the surface go? That's of f of 2 minus 1. The function was x squared, so I've got 2 squared. Plus xy is 2 times minus 1. Plus y squared is minus 1 squared. And minus 3x is minus 3 times 2. It's 4, 2 plus 1, 6. It looks like it's minus 3. So there's a local minimum of this function of minus 3 at the point -1. That's the idea. Any questions on that one?
So the minus 3 is that's the min, or yeah, that's the min, and the 3. Wait, and the 2 comma -1 is
This is the
critical
minimum
point.
z value. It's a polynomial surface, something like this. Oops. And at the point, let's see, I guess it should be over here. X, Y, Z. At the point where x equals 2 and y equals -1, right here, there's a local minimum value of -3. I drew it in the wrong spot. Oh, I can't draw this in the right spot, can I, for my life? So it's down here somewhere below the point. X equals -2, y equals 1, and z equals 0. I'm sorry, 2, -1, 0. It goes down to a z coordinate of -3. So the minimum is -3, and it occurs at the point -2, 1 in the xy plane. We don't bother to put the z coordinate in. That's just for the picture. Okay, well, let's try another one here. I guess we'll have to do the global extrema next time, it looks like. Oh, wait a minute. Okay. All these classes starting at 15 minutes continue to get me mixed up. Once in a great while, let the class go at the wrong time. Not very often. Once in a great while. And this one finishes at 15:10. Well, let's go. All right. All right, let's try this one now. This time f of x is x squared plus y squared plus 2 over xy. That's a little harder one. We won't get linear equations for the partial derivatives equal to 0. You do the two-step method, right? It's easy as dancing, right? You find the critical points. By setting the partial derivatives to 0. So you first have to calculate the partial derivatives. Fx is 2x plus 0 plus derivative of x to the minus 1 is minus 1x to the 2. So I get minus 2. So I get minus 2 over x squared y is the partial derivative of 2 over x. So I think of this as 2x to the minus 1. 2 times minus 1x to the minus 2. Times 1 minus 1 is this one. So there's fx. Here's fy is 2y. That's the same plus minus 2 over xy squared. The same calculation. Then I need the second derivatives. Fxx is partial derivative with respect to x gives me 2 minus, well, derivative of x to the minus 2 is minus 2x to the minus 3. So this becomes plus 4 over x cubed y. Minus 2 times x to the minus 3 all times 2 over y. Fy, partial of fy, y get 2 plus 2 over x y cubed, 4 over x y. And then I need the next one. So f x y. So I take partial of fx with respect to y, for instance. Minus this one, the derivative of this one will be minus 2 over x squared has minus 1 minus 2 becomes plus 2 over x squared y squared. There's fxy. So what are the critical points? I need the first derivative set equal to 0. So these I don't need yet. I'll just use these. I'll set 0 equals 2x minus 2 over x squared y. And partial respect to y equals 0. Both derivatives equal 0. 0 equals 2y minus 2 over x squared over xy squared. These are nonlinear equations in general. There's no good way to solve these. I'll say on these nonlinear equations, generally the best way to do them is to solve for a variable one equation and substitute it into the other. So try doing that. Maybe this one I could solve for y. It only occurs once, right? So I could say this one is 2x equals 2 over x squared y, right? And once more, I can divide by half and write 1x equals 1 over x squared y. So this equation applies this one. And now if I multiply by x squared, I've got x cubed equals 1 over y. And if I take reciprocals, I have y equals 1 over x cubed. Be very careful on this because I just left out some solutions, actually, if you think about it. Well, I could have, let's say. When you multiply both sides by x squared like this, you've assumed that x isn't 0, right? You can multiply both sides by any non-zero number. So I assumed x wasn't 0. That's okay because the derivative at x equals 0 doesn't exist anyway, right? But be careful on that. Make sure you check all the points. Same thing here. If I solve for this one, I've got y equals 1 over x, which is y cubed equals 1 over x. X equals for y cubed. So I solve for each variable in terms of the other. Now what I can do is just substitute from one of those into the other. I could have done that in here, couldn't I? But I'll put those together any which way I can. Let's replace y in that equation with 1 over x cubed. Then I've got x equals 1 over y cubed, but y is 1 over x cubed. So this is x equals x to the 9th. How about that? And I can solve this by factoring, right? I can rewrite this as x to the 9th minus x equals 0. I'll write that as x times x to the 8th minus 1 equals 0. And this factors further. All right, that's the difference of squares. You can write it as x times x to the 4th plus 1 times x to the 4th minus 1. X to the 4th minus 1 factors further. It's x times x to the 4th plus 1 times x squared plus 1 times x squared minus 1, which factors further as x plus 1, x minus 1, all equals 0. So if I factor it all the way, I have that. I get two solutions. X equals -1 makes this factor 0. X equals +1 makes this one factor 0. So x is 1 or -1 is the only solutions on that. Right? Those are the x coordinates, but now I have to find y coordinates to go with it. If x is 1, I put it into this equation here, y must be 1. If x is -1, I put in this equation, y must be -1. So there's 2 points, 1, 1, and -1, -1, by taking this and putting it into here to find y. These are the critical points. All right, first step, okay. What makes this hard is there systems and equations have to by hook or by crook solve them. Usually it's all from the equation and plug it into the other. So you can also do in the linear equation work that you need to do. Now I need my second derivative here to compute d at each point. So check each. There's 2 points to check this. I'll take d at the point 1, 1 gives me, well, let's see, d was, I need to write d first. I didn't write it yet, did I? D, recall, is fxx fyy minus fxy squared. Right? So we write that out. It's this one, 2 plus 4 over x cubed y, times this one, 2 plus 4 over xy cubed, minus this one squared, plus minus 4 over x to the 4th, y to the 4th. Wow. Good thing we have easy points to plug in, plus and minus 1. These are big powers. So now I need to compute d at each critical point. So I check each with this d that varies from critical point to critical point this time. So I guess I wrote these out. I don't need these. But now D at the first critical point, D at 1, 1 is just 2 plus 4 over 1 times 1 is 2 plus 4. 2 plus 4 over 1 times 1 is 2 plus 4. Minus 4 over 1 to the 4th times 1 to the 4th is 1. So it's 36 minus 4 is 30. I'm going to have a min or a max here if the second derivative is positive. Let's see what the second derivatives are. Let's just do fxx. It doesn't matter which one you do with that. fxx at 1, 1, and we still have it up here, is 2 plus 4 over 1 times 1. Is 6 is positive. Second derivative is positive. With D positive, by part 1 of our second derivative test, we have a local minimum at 1, 1. All right. It is positive, so it's consistent concavity. The concavity is up in the x direction, so it's also up in the y direction. And we have a local minimum. Now we have to check the other one, right? We'll take D at minus 1, and we notice again we get 6 times. Oh no, we don't. Yeah, okay. 2 plus 4 over 1 is 6. 4 over minus 1 times minus 1 is 6. 2 plus 4 over minus 1 times minus 1 cubed is 6. Minus 4 over minus 1 squared minus 1 squared. 1. Again, I get 32. So this one is also a local minimum. And this brings up an important point. Sometimes you can see from the symmetry in the function that the 2 points are going to give you the same value. If all the values are squares in there, then it's going to be right an even function in both variables, and you can just flip it across and with symmetry say, well, there's a local minimum at 1, 1. There has to be a local minimum at minus 1 also. But here we went through the whole thing. And if the local minimum is the value of the original function, the local min at minus 1, and it's half of minus 1. Let's see, was minus 1 squared plus minus 1 squared plus 2 over minus 1. That was the function. X squared plus y squared plus 2 over xy is 1 plus 1 plus 2 is 4. So you have a local minimum of 4 at the point minus 1, and also here 4. If D is less than 0, then you get a saddle point. Okay, so that'll do it for the relative extrema, local extrema. Then the question comes up, what if you want a global extremum, right? What do we do in calculus 1? The question, once you see that, you can extend it for this. in Calc 1, you have this theorem. If you had a function like this on an interval from A to B on a closed interval, every local, if it's a continuous function on a closed interval, then it has a maximum. That's nice to know when you start, right? And it occurs each occurs either at an endpoint or an interior critical point. So I see one interior critical point where the derivative is 0, C, and there's two endpoints. And so on this closed interval, on a closed interval AB, with f of x, there is a highest point and lowest point, a global maximum, also called an absolute maximum. That just means a highest point and a lowest point over all the domain of the function, not just a locally extreme point. Each occurs at an endpoint, A or B, or an interior critical point, where the derivative is 0 or doesn't exist. All right, that was calculus 1. There's a nice analogy to that. You can get this. That's for a function of one variable, y equals f of x. In calculus 4, we'll say this on a closed bounded domain. Just like this is a closed bounded domain of a function of one variable, we'll demand a closed bounded domain of a function of two variables now. With, just like here, f continuous, but now it's continuous function of two variables. Can you guess what the next line is? It's like calculus 1, right? It has a relative extremum. If it's continuous, you don't have a sudden fit in it where it jumps suddenly, and it's closed and bounded, then you have this kind of a picture in your mind. Here's your closed bounded plane region, D for domain, let's say. There's a surface up here above it that's continuous, so it doesn't suddenly jump anywhere. There is some point where it has a global maximum. Maybe it's this one right here. X naught, Y naught. And there is some point where it has a lowest point, maybe right here. Might be on the boundary. X1, Y1. And just like calculus 1, there is a maximum minimum, and it occurs either in an interior critical point or a boundary point. Max, and then occurs. It could be that it's repeated, right? There might be 2 points at which it reaches the highest value, or an infinite number of them. It just says there is a maximum and there is a minimum, which doesn't say how many. Each occurs only at a critical or a boundary point. It's just a function. It's just a region of two variables instead of one. Well, it's the same theorem, just analogous at least. I hope this picture helps. It shows you how the minimum here is on the boundary in this case, and the maximum is an interior critical point where it has a horizontal tangent plane. I need to tell jokes in there, something like that. Right. So now let's find the global max and min on this one. Example, f of xy equals xy minus 2x is on a region, R we'll call it, or I called it D for domain before, they called it R in here, so I'll switch to that, is the triangular region with vertices 0, 0, 0, 4, and 4, 0. 0, 0, 4, 0, and 0, 4. Triangle, it's this one right here. I maximize this function over that triangle. Actually, this is pretty long easy one compared to what you can do or be asked to do. I just need to do the same thing we did in calculus 1. The strategy for global extrema is to find all the critical points and all the critical boundary points, I'll call them, where you might get a local min or max on the boundary, and just plug them all in. I haven't said what a critical boundary point is. Basically, you take the boundary and you write it as a function of one variable. It becomes a function of one variable. You minimize or maximize it by calculus 1.
Does R stand for the reals in this?
No, I'm sorry. That's why I said I changed it because they use R. R stands for region in this case. If I mean the reals, I'll drop boldface like that with 2 bars. It's what I've been writing for D, the domain of the function. What I got here, this is to go up at this point. Yeah, thank you. So this is a continuous function. How do I know it's continuous? This is one thing you should get out of the course. It's a polynomial in 2 variables, right? Polynomials are all continuous. I have to get rid of this all words. So there's a polynomial in 2 variables. I know instantly that and it's over a closed boundary region. I know instantly it will have a local max and min. So continuous. Closed means it includes its boundary. Boundary means it doesn't go off to infinity anywhere. Therefore, 3 dots mean therefore in mathematics. It has an absolute maximum, global maximum, I think I just called it. The same thing. Global max and min. What's the strategy for the global max and min? You start off with the same first step. Find the critical points, interior. But then the second step is a tango or something, right? The second step is to just plug all of these in with the critical boundary points. Plug in with critical points in the boundary, which I'll just do by example here. And the largest is the max and the smallest is the min. You just have to check them all. Plus there's an infinite number of them. That won't be the case on any of these problems. All right, so one, what are the interior critical points? I set the partial derivative is equal to 0. I'd say fx, partial respect to x is y minus 2. Fy is x. And I don't need the second derivatives here. I'm not doing the second derivative test. I'm just checking the critical points. So the critical points are 0 equals this partial derivative and 0 equals this partial derivative. Should have left more room, huh? So if 0 equals y minus 2, that says y equals 2. 0 equals x, that says x equals 0. Sometimes you'll get a point that's outside the domain. Let's see if it is. No, 2 zeros are in the domain. It's right in the boundary here. Oops. Yeah, 0, 2. Like that. So we have to check that. Well, it's not an interior point. Actually, we don't have to check it. It's not an interior point. We don't need to check it separately. No interior critical points. This isn't really a tangle. A tangle takes more than 3 steps, like more than 2 steps. It's a different. That's the point. All right. Step 2, we simply plug these in. Oh, I'm sorry. I need to get the critical boundary points. Critical boundary points are tricky. Hope I have enough time. If not, we'll finish it next time. What you have to do is write parametric equations along each boundary. Here was the boundary. It was this triangle. It went up to 4 on the y-axis, 4 on the x-axis. That looked like that. So if I call this C1, and I call this C2, and I call this C3, when you say parametric equations for C1 along C1, I can put x equal t and y equals 0, and let t run from 0 to 4. That's a really easy way to do it. Do it a different way, but that's the easiest one I can think of. So let x equals t, y equals 0. That will flip out this boundary, C1, right? Along C2. Now, let's see, this equation, this line, since it goes through 4 and a slope minus 1, y equals minus x plus 4, right? Slope minus 1, y equals mx plus b, slope minus 1, y intercept 4. There's that equation. So along C2, I can put x equals t, y equals 4 minus t, right? Put x equals t and then put it into this one. And again, t goes from 0 to 4, so that x goes from 0 to 4. There's parametric equations for the skew side, if you will, of the triangle. And then finally, along C3, I could put x equals 0 and y equals t, and let t run from 0 to 4. Let's see what critical boundary points I get now. The book does not really do much with this. It doesn't show you how to find the boundary points like this in detail. I think it's just trying not to be too detailed. You need to be honest. Now, those are the parametric equations for the curves. So, if I think of g of t, a function of one variable, is f of x and y each as functions of t along a curve. This gives me parametric equations for z as I move along the curve. Suppose I go along C1, let's see, F was, let me go back and look it up here again. We didn't get the right. Oh, there we go. X1 minus 2x. So along C1, if you like, G of t equals F of T0. But F, I already forgot. X squared minus XY, wasn't it? XY minus 2x. Yeah. XY minus 2x. So it's T times 0 minus 2 times T. There it is. You just have to find what's the maximum and minimum of this one along T going from 0 to 4. And look, this is on a closed interval, finding a maximum minimum of a function of one variable. So you use your techniques from calculus 1 and you just say, by calculus 1, oh, this is just a line, right? Y equals minus 2t. So its maximum, this is kind of negative slope. The maximum occurs at 0, and the minimum occurs at 4 because it's going downhill. You just think it's a line. There's no critical points in the middle. So you just plug in the endpoints. By calculus 1, you have the minimum at 4, at t equals 4. At t equals 4, x equals 4, and y equals 0. It has a maximum at t equals 0. It's a negative slope. It looks like this. T versus g. It's the line y equals minus g equals minus 2t. And it, so it's got a maximum of 0 and a minimum of 4. That's what I'm thinking in my head. I don't have to do the derivatives. The first derivative is -4. There's no critical points. So you just plug in the endpoints. Right, goes on. So maximum at t equals 0, and then I get 0, 0. Which is 2x minus xy. I can't remember my example. It's getting too late at night. Xy minus 2x. So it's xy of t times 0 minus 2t. Plug it into here. It's minus 2 times t 4. And the maximum is minus 2 times t is 0 is 0. Minimum minus 8 at the point towards 0. Maximum of 0 at point 0, 0. When you move along, I better draw it again. C1. Now we try C2, and I'm out of time. Wait, I'll say C2. G of t is f of t4 minus t. Plug those in. And let's see, the function function is xy minus 2x, right? So it's xy t times 4 minus 2x times t. So it's minus t squared plus 2t. This one has an interior critical point, right? So you set the and you find, oh, there's a critical point at t equals 1 in the middle. So it's going to be right here. At t equals 1 on the second curve, you get 1, 3. So I guess it's this one. Well, we're out of time, so let's say this. This is what you have to plug in. You have to plug in these 2 points because these were critical points along C1. Plug in this one because it's a critical point on C2 and also the endpoints. And I think on C3, this one in the middle, 0, 2 comes out to be a critical point if I remember. I'll have to try it. I'll put a question mark on that one. But you just plug these 4 or 5 points in and see which one gives you the maximum and see which one gives the minimum. That'll be the absolute max and absolute min for this function. Thank you for hanging on to the end. I know it's very late at night. If you want, I'll stay on for a couple minutes, ask questions. Otherwise, I'll see you On Monday.